Recording in progress.
So in last class, we talked about a lot of theory part. And I get it. That was very boring because we talked about the SVD, mathematics of SVD. Not only that, we actually went through the book page by page, and I kind of explained what that author was trying to say so that when you try to solve assignment 3, you know exactly where to go and look for the information that you need to solve the assignment. You'll thank me when you start working on assignment number 3, perhaps not now. But in today's class, what I want to do is I want to show you the most important part, which is the practical application of all the math that we talked about. That math is great, it's fantastic, and to the point that it's beautiful. But we need to know how to use those mathematical techniques. And once we talk about in today's class about practical applications of all those techniques, then you will realize that the theory would make perfect sense. And we are going to do the exact same thing when we look at compressed sensing, randomized linear algebra. Then we will look at the machine learning, artificial intelligence, reinforcement learning, and lot of tools, Fourier transform, Wavelet transform, all that. So there is a theory part that may sound boring, but please understand, once you start looking at the practical applications, things will become super clear. So let me quickly go to the recap, saying that what is the whole purpose of this SVD? Singular value decomposition is basically a tool that would allow us to solve a rectangular system of equations. Does anyone have any questions? So singular value decomposition allows us to solve rectangular value of system. It also tells us what are the most important or significant part of the data. And usually that data will be represented as a matrix. It could be a 2 by 2 matrix or 3 by 3 matrix, or it could be matrix in multiple dimensions. So we can only visualize the matrix. So think about the matrix where it has entries in X, entries in Y, and entries in Z. So you actually have a data cube, and that you want to analyze. But that is not the end of it. You could have data in 4 dimensions, 5th dimension, 6th dimension. That is mathematically possible. You cannot visualize it, but it is possible, and we'll talk about it when we talk about the tensor decomposition. But what I'm going to do is I'm going to show you the practical applications of SVD and how we can use it for our purposes. So if you don't have your Matlab up and running, I would strongly recommend open Matlab. So if you don't have Matlab open, please open Matlab, and the Matlab would open. And I'm going to say clear all PLC. And then I want you to go back to your desktop, and then you would see Matlab L4. So this is where all the SVD code is located, SVD and PCB. Everybody open this folder. Any questions? Online students, in-person students? So first and foremost, where is the folder? The folder is on the canvas. So it, okay. Yeah.
Really quick, the file components such as like the JPEG, do we have to make sure that's properly sorted inside the folder?
No, I wouldn't worry about it. I'm gonna go through sequence. I made sure that when code will run, and it will take the right data set. So don't worry about it.
Okay, so just leave it in the folder.
Just leave it the way it is. As long, can you, everyone, do you see what I have here? So now pay attention. So first thing, we are going to start with a very simple problem. Double click on SVD basics. This is the simple command that would find the SVD. And I'm going to do, I'm going to show you. So first, step one, create a random matrix. So X is a random matrix. And then can you see this matrix has 5 rows and 3 columns. Your random matrix may look different than my random matrix. That's why it's random. And just so that you know, I gave extension on the Matlab assignments, by the way. But it's not ideal because from this class onwards, we are going to use Matlab extensively. So if you are not familiar with Matlab, it may be difficult to follow. Okay, so this is 5 by 3 matrix, and I'm going to create, I'm going to do the SVD. SVD will have a left singular vector, the singular values, and then a right singular vector. So U stands for the left singular vector, S stands for the singular value, and V stands for the right singular vector. Now what I'm going to do is, I'm going to run this code. I'm going to ignore the semicolon, so you will see how big that is. I'm going to ignore. So I would say evaluate selection, and you will notice that I got U, and please note U has 1, 2, 3, 4, 5. U has 5 rows and 5 columns. 1, 2, 3, 4, 5. S has 5 rows, 3 columns, and V has 3 rows and 3 columns. Does everyone understand this? Yeah.
So just really quick, the U is the U being almost like transposed, or well, not transposed, it's being like rotated over, so
that matrix multiplication can make sense. So
yeah,
SVD decomposition is what? U, S, V transpose. That is what the SVD decomposition is. That matrix multiplication will not yield proper results unless these values or these dimensions match. But here is the key part. Since U is a square matrix, okay, there are 5 singular values, by the way. Yeah, actually, we'll talk about it in just a second. So let me talk about it. So first and foremost, I want you to understand this U matrix is a square matrix that can be inverted. If you were to find out the norm of U, that will become 1 because it's an orthonormal matrix. If you were to find the norm, matrix norm of V, you will see it's an orthonormal matrix. And to answer the question, there are just 3 singular values. Everything else is 0. Now, what does that mean? For a second, I want you to think about it. What that means is the most important information in the matrix. This is super important. The most important information in the matrix, it contained in first 3 rows of U and first 3 columns of V. Everything else can be ignored. What does that mean? It means rather than dealing with 5 times 3, that big data matrix, I can chop it off, shrink it, compress it, and still I would be able to recapture all the data. So how do we achieve that? So there is a Matlab command which talks about economy sized SVD. Matlab is smart. What, as long as you add econ, then see what happens. Econ, right click, evaluate. Now, can you see that Matlab actually gave you a U hat, which only contains first 3 columns, and Matlab gave you V hat, which contains only first 3 rows. Everyone understood this? Okay, I want you to first run U hat, S hat, V hat. And then I want you to compare S hat with S. Here is your S. Can you see the last 2 rows are zeros? And when we did economy SVD, those 2 rows are chopped off. So what it means, now for a second, I want you to do this exercise, and that would kind of make sense. So SVD by definition is, I'm gonna show you, U hat multiplied by S hat multiplied by V transpose. Do you agree with me? So what I'm trying to do here is I'm trying to multiply U hat, S hat, and V hat. And once I enter, I got this matrix 1, 2, 3, 4, 5, 6. And what this SVD is telling me is this guy has all the information contained in this guy. This guy has all the information contained in this guy. And I want you to verify that is the case. I would give you a minute to take a look at that.
So when you say 3,
now let me explain to you the practical issues that you could have here. So imagine that you want to take this data and pass it around. The number of the storage bits that you need to store this matrix will be exponentially decreased if you were to perform SVD. And you may not believe me right now, but bear with me for a second and it will make clear. But before I go further, I just want to make sure that you guys, everyone, is able to run the SVD and economy size SVD. Is it giving you some answers?
Yeah.
Okay. Now, I want you to open the second part, which is dog compression. Yes, economy SVD contains all the information of X, even if it has lower dimension. And bear with me for a second. This point will be absolutely clear after this example. Bear with me. So what I'm trying to do here, I'm going to go line by line to this code. Clear all, close all CLC, clear everything, clear all the variables. So once I execute that, please note the workspace will be cleared. So if I clear that, you can see the workspace is cleared. Command window will be cleared. There is nothing. Line number 3, there is an image of this dog. So if you double click, there is this beautiful dog image. I want you to double click on that image and you'll realize that this image is nothing but an actual matrix. This image is an actual matrix. And this matrix, actually it's not a matrix, it's a tensor. Why it's a tensor? Because it has 3 dimensions. Can you see that it has 2000, 1500 and 3? Why 3? Because color image is constructed by superimposition of RGB. That's why basically what you have the image with red markings, you have image with G, and you have image with blue. When you combine, when you look from front, those colors get combined and you get this beautiful color image. You agree with me? So this is a huge tensor, not matrix, because it's in 3 dimensions, it's a tensor. So what we are going to do, and this is actually a very small image. It is not 12. Actually, if you look at the size of that image, if you double click, it will actually tell you the properties, and you will see that this is not a very high resolution image. So this is not a very high resolution image, but the amount of data that image contains is huge. Now what I'm going to do is I'm going to read this image. A is equal to IM read. IM read stands for image read, and basically what it will do is you're welcome to omit the semicolon, and you'll see as soon as you do image read, that image data will be stored in a 3-dimensional matrix form that you can manipulate. So if you want to see, I can do that. I can just say here, and Matlab, that is the matrix that Matlab is reading. Can you see? It's a huge matrix. Now, for this example, what I'm going to do is, rather than working on the tensor, which means rather than working on RGB, I'm going to convert this image into grayscale so that we would just have a matrix. But this approach will work for a tensor. So what I'm going to do is, I'm going to take that RGB image and convert that into grayscale. So there is a Matlab command that will take RGB image and convert that into grayscale. So everyone understands how this image is captured. You have a matrix, you have another matrix, and you have another matrix. So first matrix contains the shades of R. Second matrix contains the shades of G, green, and the third matrix contains the shade of blue. When all these shades are superimposed, you get that color image. So basically you have that tensor. I'm going to convert that tensor into a matrix. So evaluate, and again it will run. But now if you were to look at, if you were to do size, so yeah, now we lose the color information. But so size, and for this couple of first few examples, I'm gonna go very slow because I don't know how comfortable you are with these various Matlab functions. So if you don't understand, stop me and ask. So if you were to do size A, can you see 2000, 1500, 3? If I were to do size X, can you see? So now that tensor has converted into matrix. Now this NX is just the sizing, so I wouldn't worry about it. Line number 5 and line number 6 is just for the image. So basically now this is going to plot the image. This is just the Matlab function. So this is the grayscale image that we have. But still, this is a huge image. This is a very big image. So what I'm going to do is, I'm going to perform three channels turn into one channel. That is correct. Any other questions? So what I'm going to do is I'm going to do SVD over here. So once I do SVD, it's actually running the exact same command. This is not an economy SVD. This is a full blown SVD. And the reason I'm doing that, I'll tell you in just a second. So evaluate selection. So SVD is performed. Now what I want to do is in the next few lines, what I have is I have R is equal to 5, R is equal to 250, and that 0 you can ignore. So what I'm going to do is I'm going to retain small part of that SVD. So basically I'm going to truncate. So when I say 5, what's going to happen? So I have this huge SVD decomposition, and I will show it to actually, let me show it to you what that is, that looks like. I have this S. Can you see that this is the big S matrix? But have you observed that in this S matrix, there are tons and tons of zeros? Those zeros can be ignored. So what I'm going to do is I'm going to truncate the U vector. I'm going to truncate the SVD, and I'm going to truncate the V vector and try to see if I can capture the image that I started with. So what I'm going to do is I'm going to keep just first 5 columns, first 5 singular vectors. I'm going to maintain just first 5 singular values, and then I'm going to construct the image. So check this out. Highlight this and run. So this tells you when I'm just retaining the first 5 singular vectors, I get some shade, some capture. I get, and again you need to convert this into RGB, but basically, and if you were to do the first 250 singular values, then you are going to get some additional features as you start increasing. As you start increasing the number of singular vectors and number of singular values, you will see that more and more details become evident. But here is something point that I want to explain. Can you see that I'm retaining just first 250 singular values? I'm retaining first 1000 singular values, but the quality improvement is not significant. It means I could potentially just retain a very small part of that matrix and still be able to capture the most important information. Everyone understood this? Before I go any further, I just want to make sure that you have gotten these same results. Yeah.
So in general, this would be like some loose image.
Can you repeat your question? So that
So we have in file types, we have compressionless and then like loose images.
yes, so this is exactly what they do in compression, but this is the crudest form of compression. This is not efficient. There are advanced techniques for compression, but this is the basic, very basic image compression. Any questions from my online students? Now, next thing is, how do I represent this information? And sometimes if you come from computer science background, they call it an entropy. So they call, or if you study information theory, basically they call it entropy. How do I know that how much information or how much entropy is retained? For that, you can actually plot the singular values, and then you will see that this is how it looks like. So on the left hand side, you will notice there is no legend here, but I want to tell you that what it means. If you were to retain 1,500 singular values, you will get perfect reconstruction. But as you start decreasing, maybe at 1,100, you are gonna get still very good reconstruction. And that's what is shown over here. So you have the law of diminishing returns, and it actually is showing the decaying singular values. So as you can see, the first singular values, they are super duper high, and the last singular values are very close to zero. So you can, for practical purposes, you can ignore those singular values and singular vector and achieve compression. Everyone understood this? Any questions? Yes.
Could you please go over the first graph again?
This graph.
Yes, sir.
So what you have in the first graph is basically I'm plotting, and actually it might be clear if I were to just look at the Matlab script here. If you look at the first subplot, I'm plotting the singular values. S are the singular values. And in second plot, I'm actually plotting the cumulative singular values because they actually retain, they tell us how much information is retained. So as you can see, the first few singular values are very, very high compared to last singular values, which means majority of the information is contained in this region. And that's what is shown over here. As I start including more and more singular values and singular vector, I get perfect reconstruction. But for practical purposes, this perfect reconstruction is really not required, because once you follow the, and we'll talk about it a little bit later, once you follow the principle of compressed sensing, you can still send out a small piece of information and reconstruct the information that is missing. That is what is happening all the time in 5G wireless networks. If you think about the amount of data that you're, or exactly, this is exactly what happens when you stream data from, you try to watch movies from Netflix, if you try to watch movies on Amazon Prime, because that data, if you want to see the real-time reconstruction, that data needs to come very fast. And sometimes what you have to do is you have to play some tricks. You have to compress the data, uncompress the data, and all those things, they happen in real time so that the reconstruction is accurate. Now, for a second, think about the 4K rendering. If you are sending 4K data using some sort of wireless or wired network, think about the amount of data that is sent at reconstruct. Okay, someone is trying to connect dot. Yes, that is correct. Okay, so once this is done, then what I want to do is, the next example is I want to talk about this SVD we talked about is good. But what is the geometric interpretation of SVD? I mean, how do we see what is this transformation doing to the data set? And if you are in my robotics class, or if you are in my robotics class, recognize these are the exact same rotation matrix that we talked about. So you have rotation about X, rotation about Y, and rotation about Z. And if you don't follow what these rotations are, that's totally cool, because this is just a toy example. So what I'm going to do is, I'm going to run this code. I'm just going to run this code. And I would encourage you to run that code. Give me a second so that I can plug in my charger. Okay, so when you run this code, it actually performs the transformation, and then I want you to plot this sphere. So this is exactly the geometric representation of SVD. What SVD does is think about that you have a data set in 3 dimensions. SVD will actually sort of squash the sphere and elongate the sphere along the principal dimensions, which means what SVD will do is SVD will look at this data set, then it will identify what are the most important basis vectors that can be used to represent this data and actually bring out the true picture. So SVD will take this data set and actually decompose that into its principal components or the significant components. So this is the geometric representation of SVD. So probably it would be more instructive to look at the visualization of SVD. And again, this is just for visualization. There is no underlying code to understand. If you run open SVD visualization, run this code, and then it's going to give you a very nice picture. So I want you to think about this picture, and actually you can interactively rotate this. So think about it that you have a data set which is at the center. And what SVD is going to tell you is SVD is going to tell you the most important components of this data set. So this data set, since it's a 3-dimensional data set, it has 3 important axes, X, Y, and Z. So SVD will give you basis vectors so that you can reconstruct or plot this. Think about it for a second. It's like every data point there represents a vector, could be the force in 3 dimensions. And now what you want to do is you want to find out the component of the force perpendicular to each other. So what directions or what axis would you choose so that each vector can be resolved into its most basic components? And those dark lines are nothing but the important directions. Now, why is this all important? And this is important from an application point of view. So let me start with a very simple application, which is called as the linear. Yeah.
So the principal dimensions you're talking about, are those the same thing as the eigenvectors for those particular columns of the?
Right. Now, eigenvectors. So basically, as long as your matrix, or for that matter, tensor, is a square matrix or a cube tensor, you have eigenvalues and eigenvectors. But if your matrix is a rectangular matrix, and if your tensor is like a brick, then you don't have eigenvalues or eigenvectors.
Because in this case, it was looking like the USV, the S was looking like eigenvalues, so that's why.
So once again, I'll repeat. Eigenvalues for a square matrix are the singular values for rectangular matrix. Eigenvectors for square matrix are similar to the left singular vectors and right singular vectors for a rectangular matrix. Everyone understood this? That is the key concept. Now, what I'm going to do is, I'm going to actually this needs a little discussion before I solve this problem. I'm going to switch to the whiteboard, and I will try to explain what is happening in this problem. So I'm going to switch to the so this is very important, and I think it would be instructive for me to explain what is happening in this problem. First and foremost, please understand that we are talking about singular value decomposition. So if I have a rectangular matrix X, so this matrix is a rectangular matrix, maybe 5 by 10. This is a rectangular matrix. You cannot find eigenvalues of this matrix, but what you can do is you can use SVD and decompose this matrix into, you can use SVD and decompose this matrix into U, S, V transpose. Do you agree with me? Everyone agrees with me what we talked about? So you can actually decompose this into this matrix. And for this X to be decomposed properly, remember, this is a square matrix. This is a square matrix. And this is actually a rectangular matrix. So the first, this U is going to be 5 by 5. This is going to be 5 by 10. And then the last matrix is actually the transpose of it is going to look like 10 by 5. Only then, when I multiply U times S multiplied by V transpose, I'm going to get 5 by 10. Do you agree with me? These dimensions must match. Actually, it's transpose. So I'll explain this to you in just a second. So in the decomposition. So what's going to happen here is, if I have an equation, system of equations, yeah, we should be 10, 5. Just a second here. Let me try to explain this and I'll answer your question. So I have a question. I have a decomposition to perform on the equation, system of equations, where A is a rectangular matrix. Yeah, actually I made a mistake here. So I have a rectangular matrix here. And what I want to do is, if you recollect in last class, I talked about solving this matrix comes from A transpose A. X is equal to A transpose B. And then X is equal to inverse of A transpose A multiplied by A transpose B, and you can get the solution for X. Now what I want to show you is, you can Yeah, P should be, G should be, yeah, I'm making a mistake in these dimensions, but I'll explain to you what I'm trying to do here. And we can verify those dimensions when we go into the MATLAB. So this is how you will find X. So this is one way of finding X. So if you want to solve a rectangular system of equation, this is what you do. Now in this MATLAB code, what I'm trying to do is, I'm trying to solve AX is equal to B using the singular value decomposition. So AX is equal to B, where I'm going to decompose A is equal to U S V transpose. So first I'm going to find out the SVD of A. This is going to be U S V transpose. And please note, this guy is known. So this is also known. B is known. And X is actually unknown. But since U and V are both rectangular, I mean both square, and I want you to see this, and dimensions will work out very nicely. So what I'm going to do is, I can find out the first inverse of U, U S G X is equal to, once again, X is the unknown, U inverse B. This can be solved, and this guy becomes identity. Then I have S Vx is equal to U inverse B. And what I can do is, actually I can take this guy and then transfer that, something like U. And please note, the most important part here is U inverse is going to be U transpose, because it's an orthonormal matrix. So you're going to have U inverse B, and then what you do is you perform once again the conversion. So S times V inverse times U times B, and then basically you have X, and this is basically becomes V inverse S inverse U B is equal to X. So what I'm trying to do is, I'm trying to solve this linear system of equation using MATLAB, and I will confirm, I'll tell you about the dimensions in just a second. So yeah, so actually I made a mistake in dimensions, but let me explain that with the MATLAB code. So bear with me just for a second, and I will explain it to you what is going on. So bear with me just a second, and I will tell you what the dimensions are going to look like. So you should be seeing my code. So what I'm trying to do here is, the thing which I talked about is here. G S inverse U times B. Okay, so because V inverse is equal to V transpose, so this is what is happening. So what I'm going to do is, I wanted to show you that what trick I did here to solve the linear equation, which is the rectangular system, is done over here. And we are going to go through this code step by step. But so what I'm trying to do is, rather than doing inverse of A transpose A, I decomposed A using singular values decomposition, and then I inverted those step by step. So let me first plot this. So this is the actual line. And what I'm going to do is, if you follow this, you will notice you have this noisy data set, which is, these are the points that actually indicate the rectangular system of equations that we talked about. The actual solution is shown by this dark line. And if I were to look at the solution found out from SVD, is shown by the dotted line. What I'm trying to say here is, this is exactly solving the least square problem, but instead of doing A inverse of A transpose A, which we talked about in last class, what I'm doing is I'm using the singular value decomposition. So let me talk about the code. So what you have is, you have some data set. And what I'm trying to do is, I'm trying to find out it will be clear in just a second. It will be, oh, okay, yeah. Zoom is not sharing the windows. That's an issue. Just a second here. So let me show you. So I need to share. New share. And what I need to do is I need to share this figure. So this is how your figure should look like. And this is just so that the online students can see what is going on. So red points. So what I'm trying to do here is, the data set is given, and that data is represented by red marks, so crosses. And what I want to do is, I want to fit a line that actually very well goes to the least square. So what I did least square type of analysis using two techniques. I used the baseline Matlab code to find the exact equation for that least square. And then I used the singular value decomposition to find out the equation of the straight line. So this is nothing but something called as the linear regression. This is linear regression, and linear regression can be done using the techniques that we talked about, inverse of A transpose A, or you can use a singular value decomposition. Now let me show you the important example. So clearly, you may say, why am I doing this? I don't see any significant advantage over here. And you're absolutely right. For a simple linear regression, you may not see a significant advantage. However, it would be apparent when you are going to do a regression that is multilinear regression. And believe it or not, multilinear regression was the essence or some of the first machine learning AI type of machine learning concepts were based on the multilinear regression. So here is the idea. So there is certain phenomenon that depends upon maybe 3 or 4 factors, and you have the data set. Now the question is, if you get some different parameters, what is going to be the outcome? So think about it something like this. In this example, what we have is, we have something called as the data for the Portland cement. So what we are trying to do is, we are trying to find that there are actually 4 ingredients, and there are 13 different mixtures. So if you think about it, there are 4 ingredients and there are 13 different mixtures. So the question is, if you come up with a random combination of those ingredients, what is going to be the outcome? So think about it like this, and this happens all the time in design of experiments. So for example, what you want to do is you want to come up with a particular compound, and you have some basic ingredients. What you do is you perform something called as the design of experiment and kind of construct this matrix, which is going to be dependent on 4 elements or 5 elements, and there would be an outcome here. And then basically, if you provide some unknown input to that system of equation, what is going to be the output? This is a very classical machine learning problem, wherein you have say data like how intelligent I am and how much time do I take to crack an exam. And if you have a lot of data, then potentially you can input that if the student has an IQ of 150, if that student studies for 3 hours, most likely he's going to get 95%. Or if someone has an IQ of maybe 110, but if he studies for 7 hours, most likely he's going to get say 95%. So you can actually provide different inputs and still you would be able to get the values. So I would encourage you to look at this data, and what that tells you is it may just look like the simple regression model, but what it looks like is based on the ingredient types of ingredients and properties of ingredient, you can actually predict the amount of heat that will be generated as that cement forms. So this comes from an actual experiment. So you have Portland cement, and Portland cement has 4 ingredients. And what they did, they performed the experiments and they found out once you vary ingredient A, once you vary ingredient B, once you vary ingredient C, and once you vary ingredient D, what is the amount of heat that is generated as that cement solidifies. Now, what this means, with this information, you can specify different random compositions of A, B, C, and D, and you'd be able to predict fairly well what is going to be the heat generated. Is this clear? This may not look like much, but believe you me, that this is the first iteration of machine learning. For example, if you have housing data, so you have the housing price of a house, and maybe you have some economic marker, and you have the location. So you can actually, and again, you can predict if the economy is doing well at this particular location, what is going to be the price of a house. You can do the exact same thing on lots and lots of stuff. So this is a multilinear regression. Why this is a multilinear regression? Because there are 4 inputs and 1 output. Everyone understood this? If you go to industry, this is going to be super duper important, because in industry, what you want to do is you want to find out what is the best combination to achieve something. That is called an optimization problem. What is the best combination? So imagine that you are in a candy making shop, and then you have maybe, let me say, 3 ingredients. One is the shape of the candy. Second one is the color of the candy. And third thing is the sweetness of the candy, right? Then what you can do is you want to find out which candy would make me the most profit. So which candy gets sold quickly. So what you can do is you can have maybe 3 gradations, like red, green, blue, then rectangular, square, triangular, and then you have one more set where low sweet, medium sweet, and super sweet. what you can do is you can just perform these 9 experiments, and then it will actually tell you, that what combination gets sold at what rate. So you can play like, okay, what I'm going to do is I'm going to use maybe sweetness in between low and medium. I'm going to change the color, which is in between red and blue. And I'm going to change the shape, which is between, say, a sort of a rectangular and sort of a triangular. So some weird shape. And that should be able to give you a good estimate of how much candy or how much time would it take to sell out the candy. This is not the perfect example, but that is the point. The next thing is what happens as you once you add some noise in the data set. Clearly, the things in the practical life, they do not fall precise, they do not have precise mathematical definitions. There's always some variation, there is always some variance. So the key question is, how would you perform similar type of analysis when there is randomness involved? This is the very most important problem. So you are collecting data, but the data does not follow a trend. The data has some sort of noise. So how do you make sense from that noisy data? So the extension of SVD, and this is very important, extension of SVD when there is noise present is called PCA. Extension of singular value decomposition when there is noise present in data is PCA. So the example which I gave you about selling the candies, believe it or not, there is some randomness. So there is no guarantee that, okay, you do this, you do this, you do this, and X number of candies would get sold. Because if you were to repeat the exact same experiment the next day, it could be more, it could be less. So there is some randomness. Think about the prediction models. The prediction models will have some uncertainty. So how do you perform this data decomposition when there is uncertainty? And it will all make sense in just a few minutes. So we are just actually on the surface, but what I want you to do is, I'm going to look at PCA basic. Once again, PCA, principal component analysis, is exactly same as singular value decomposition. Only thing is the data or the matrix has some random entries. Everyone understood this? Whenever you have some sort of random data, how do we characterize randomness? We characterize randomness in terms of the distribution of the random variable. Remember Poisson distribution, Gaussian distribution, chi tau distribution. There are hundreds and hundreds of those distributions. So the first thing, when you have randomness, when you want to analyze using the principal component analysis, we take out the mean. So what we do is, if you have random some variation, we center it at the mean. So which means the mean of the data is 0. Does it make sense? So here is the problem that we are trying to solve. We have some sort of data coming to us that has randomness, and we want to analyze that data, maybe compress the data, maybe transmit the data. So to understand the principal components, I'm going to take out the mean, which means I will only be left with the variance, which means what is mean? Means average, variance is spread. Means the average of the data, variance means the spread, how close or how far each data point is. So if you look at this Matlab script, I kind of tell you that what is the relationship between the PCA and SVD. But for the purposes of this course, remember PCA is extension of SVD when you have Gaussian distribution involved. Everyone understood this? and we will actually get into the details of PCA. But that Gaussian distribution is an important underlying assumption for compressed sensing. So PCA, and it will be clear as we work through the example. So once again, the same thing. I have a random matrix, and I'm going to perform the principal component analysis. So once again, what I'm going to do is I'm going to clear all CLC and create this random matrix, which is 5 rows, 4 columns. And I'm going to perform the principal component analysis. And these principal component of this data, they are similar to the SVD decomposition of the matrix. The only difference is when you perform PCA, you actually take care of, you remove the mean, and then there is some normalization that takes place. But that you can actually relate PCA to SVD very clearly. So what I want to do is, and this would make sense. So everybody, are you able to run PCA? Were you able to get some results? Next thing, what I want you to try is PCA Gaussian. And this actually shows you what is the geometric representation of PCA when you have Gaussian data. So the only thing what I want you to see here is your variable has some noise. So basically, I just want to show you, can you see that here there is some noise? So, and I'm adding noise to it. If you run this code, and then all of a sudden, this figure will pop up. And I will show you this figure in just a second. So this figure shows you the data. It shows you the principal components of data. And what are the principal components? The principal components are shown by this red ellipse. So it's basically saying that this is my first principal component, this is my second principal component, and this is my third principal component. So what it means is, if I were to take this data set and perform PCA, and if I retain the first 3 principal components, just like the SVD what we did earlier, most of the data will be captured. Once again, I repeat. So you have this blob, which is actually a data set. And why this is a blob? Because there is some randomness involved. So that this data distribution is random. But please note, what I did is I did perform the principal component analysis, and then I have plotted the first principal component, second principal component, and third principal component. The key observation here is, just like SVD on the random data set, if I were to capture the, if I were to take the first 3 principal component, most of the data is captured. But what is the advantage? The size of the matrix, the size of the data will be exponentially less, just like SVD. Now, what are these lines? If you were to perform, for some reason, singular value decomposition, this is going to give you the first singular vector, and this is the second singular vector. Please note, they are perpendicular to each other. So what they are saying, that this data set has 2 important basis vectors, this and this. What it means is, if I want to resolve, I should be able to resolve along those principal vectors or singular vectors. So this is just a geometric representation. And let me show you what happens in the case of practical data set. So, and actually this is a very important data set. PCA describes, PCA describes similar to SVD when the data is distributed. Now, what I want to show you, and this is an example I took because this has significance in terms of biomedical applications. So this data comes from the actual data collected for ovarian cancers. The good news is this data is built inside the Matlab. Now, if you look at the description, and I gave you the description because then you can actually understand the importance of data. So this data set consists of the genome data for 216 patients. I don't know if you are into genome sequencing or not, but gene sequences, protein sequences are super complex. So if you think about the amount of encoding, amount of information that is contained in each sequence is huge. So basically, there are 4,000 genes. And these 4,000 genes, as you can see, there are multiple challenges. So what we want to see is, here is a classic problem. We know if we have particular genome sequence, then that person has ovarian cancer. If we have particular genome sequence, then that person has ovarian cancer. If we have some genome sequence, that person does not have ovarian cancer. Now the question is, what is the possible combination of that genome that would most likely be indicative of ovarian cancer? I repeat this problem again, and this problem is not simple to solve. So basically, there is, you know that that person has cancer, you got the gene, and you somehow found out the genome sequence. In that genome sequence, also there is randomness, because the other person may have same or similar genome sequence, but may not have cancer. So, and what you do is, basically, they went through this data set and they identified 4,000 individual genes and their sequence. And this data was collected to 216 patients. So the question is, if a new patient comes in, we don't know if that person has ovarian cancer or not. Or we don't know whether that person will develop ovarian cancer or not. But what we only know is, we know the genome sequence. So based on the genome sequence, can we predict if that person has or will have ovarian cancer? Everybody understood this? This is a classic pattern recognition problem, which means, so very basically what I'm going to do is, I'm going to use something called as PCA, but I would use SVD to perform PCA. So first and foremost, clear all, close all, and I'm going to load this ovarian cancer data. So I would encourage you to load this data set, and you would realize that I'm just gonna show you this data, and you will read. So OBS is actually that ovarian cancer data set, and run. We don't know. Just looking at the data set, we don't know how to decipher this code. So what we do is, we want to run something called as SVD, and you will realize things are going to become super easy to predict. And I'm going to run this entire code. Now you would clearly see that the red indicates the genome sequence that is indicative of cancer. Blue indicates the genome sequence that is indicative of no cancer. But the most important part here is, recognize there are only 3 dimensions. So 1, 2, and 3. So which means all that data set can be sliced and diced into just 3 components. So what that means, if I have a new genome sequence, I could feed that to this data set, and you will see what happens. If you look at data from this point of view, this angle, they may look overlap, but as soon as you start rotating this, you can identify a decision boundary.
They might not be able to.
Oh, sorry. So what you can do is you can, okay. So what I'm going to show you is, this is the data set. Perhaps it's not clear in here. It looks like, oh, it's a huge overlap, right? But as soon as you change your perspective, this is super important. As soon as you change your perspective, you can identify a decision boundary. And what that means is you can use this as a preliminary machine learning algorithm where you can feed a data sequence and then run the classification, and you would be able to see whether that person has a likelihood of ovarian cancer or not. And that is the very basic machine learning that you talk about. So I would encourage you to play with this code, and there is a lot more information here. So if you look at the way the code runs, finally what we are doing is we are using SVD, and with the help of SVD, we are able to decipher this impossible looking data into its core essence. And I'm going to stop here today, but I would be happy to answer any questions you may have.